Welcome back to the deep dive. Look, if you're working with large language models right now, building things, experimenting,
Hmm.
you know the headache.
Oh, yeah.
The LLM universe is just exploding, isn't it? And figuring out which model for which specific task, it's getting tough.
It really is. Do you go for that cheaper, maybe faster 8B model? Or do you really need the power and the cost of a huge 70B one?
Exactly. And it's not just about how well it works, it's the budget, right? The cost implications are huge.
Totally. And most systems try to handle this with, well, what we call a static router. It's single round,
Oh, no.
meaning a query comes in, the system picks one model based on some rules someone set up beforehand, gets one answer, and that's it. Done.
Which is fine for simple stuff, maybe classification.
Yeah, for simple things, it works okay.
Uh-huh.
But anything complex, like multi-hop question, answering where you need to connect dots, that single-shot approach, it just doesn't cut it. It often falls short.
Absolutely. Complex problems, they need, like, a sequence of different strengths, don't they? Not just a one-shot deal.
Precise.
So our mission today is to really dig into Router R1. It's this new framework, and it seems to flip the script. It makes LLM coordination dynamic, multi-stage, not just a static choice.
Yeah, the big idea here is turning that whole coordination problem into a sequence of decisions. And they use reinforcement learning, RL, to figure out the best sequence.
Okay, so less like picking one tool from the toolbox.
And more like conducting an orchestra, maybe, or choreographing a team of specialists. Router R1 learns on the fly which LLM to call next.
Tapping into their different strengths.
Exactly. Maybe one is super fluent but makes stuff up sometimes. Another is slower but rock solid on facts. Router R1 learns to switch between them and only calls them when it actually needs that specific skill.
That's a pretty big shift conceptually. Okay, let's get into the nuts and bolts then. If you're coordinating LLMs one after another sequentially, you're doing more than just routing, right? You're reasoning step by step. How did they tackle that? It sounds computationally tricky.
Well, yeah, the main hurdle is that decision. Which model do I call now? That's a discrete choice. It's A or B.
Not a smooth gradient.
Exactly. And when you make that choice, you break the continuous flow that you need for normal backpropagation-based training. The whole thing becomes non-differentiable.
Right, so standard gradient descent methods just won't work for teaching the system how to route properly. The call model step is like hitting a brick wall mathematically.
Pretty much. So Reader R1 reframes it. It's a sequential decision-making problem. But here's the really clever bit, I think.
Go on.
The router itself, it isn't some fixed external piece of code.
It's not. What is it then?
They realized, hey, what's really good at reasoning and making complex decisions based on context? An LLM.
So the router is an LLM.
Exactly. They use a capable but efficient base LLM as the policy LLM. Something like Quen 2.53b instruct or Llama 3.23b instruct.
Okay, so by making the router an LLM, it automatically gets all that reasoning, planning, context understanding capability baked in.
Right, which is exactly what you need to juggle these complex multi-step tasks.
So you've got this LLM, this policy LLM, watching the task unfold. And at each step, it does. What, you said 2 interleaved actions?
Yeah, 2 main things it cycles through. First, it does a think action.
Think, like internal monologue.
Sort of, yeah. It's internal deliberation. It happens within special tags in the context.
Yeah.
The policy LLM looks at where the task is, what info it has, what's missing, and it plans the next step. It's not just blindly picking a model.
It's reasoning about the problem state first.
Okay, that makes sense. Informed planning.
Right. And then if it decides, okay, I need external input, maybe some fact-checking or deeper analysis.
That triggers the route action.
Correct. The policy LLM dynamically calls a specific model from its routing pool. And that pool has the big guns, the specialists like LMA 3.170B or Mixtral 8x22B.
And it sends the specific query needed at that point to the chosen external model.
Yep. And then critically, when that external model sends back its response,
the router pulls that information back in. Exactly. It integrates that new piece of information using a specific info tag back into its own context, so its understanding evolves.
so it's a loop. Think, maybe route, get info, think again based on the new info.
Right. It allows the policy LLM to build understanding from multiple sources, potentially using different specialist models, before it finally generates the answer.
That's a really elegant structure. It puts the reasoning load onto the policy LLM itself rather than needing some super complicated external logic.
Yeah, it leverages the LLM's own strengths.
Okay, structure makes sense.
Yeah.
But how do you train this policy LLM? How do you teach it to be a good coordinator? And crucially, how do you make it, cost conscious? We already said standard backprop is out.
Right. So this is where reinforcement learning comes in. RL is perfect for optimizing these kinds of discrete decision policies.
Okay.
But the whole thing lives or dies by the reward function,
Yeah.
right? How you tell it what good looks like. They needed something simple, rule-based, but effective for guiding this complex stuff.
And they came up with 3 parts to this reward. What's the first one?
The first one is absolutely fundamental. It's the format reward.
Format reward.
Formats.
Reward. So this isn't about whether the answer is right, but if it followed the rules.
Exactly. It enforces discipline. The output must start with think. It must end with answer. If it uses a search tag to route a query, there must be a matching info tag later with the result.
Okay, structural hygiene.
But here's the key part. It's hierarchical. If the format is wrong even a little bit, it gets a big negative reward, -1. And crucially, all the other rewards, like for correctness or cost, gets zeroed out, wiped.
Oh, that's clever. So if it doesn't follow the structural rules, nothing else matters. It can't get points for a right answer if the process was broken.
Precisely. It forces structural stability above everything else. Because, an answer generated through a messed up process isn't reliable even if it happens to be right that one time. Better a well-formatted failure you can debug.
Right. That makes total sense. Okay, so assuming it passes the format check, what's next?
Then you get to the more standard stuff. The final outcome reward. This is basically, it was the final answer and the answer tag correct.
How do they measure that?
They used exact match, EM, against the known ground truth answer.
Yeah.
Simple binary, right or wrong. This part pushes it towards accuracy.
Okay, makes sense. Performance reward. Now, the third one you mentioned, cost. This feels like the real differentiator for practical use, the cost reward.
Yeah,
It's
this
something
is
you're not
where it
gonna-
gets really interesting, especially for anyone actually paying the bills for these models. This reward component directly penalizes using expensive models.
How does it calculate that penalty?
It's inversely proportional to 2 things. First, the number of tokens the external model spits out. Longer answers from external models cost more.
Okay.
And second, a cost function for the specific model called, this reflects the actual price, like cents per 1,000 tokens, or maybe even incorporates latency. Basically, how expensive that model is to run.
Got it. So calling a huge 70B model for a really long answer gets hit with a much bigger penalty than, say, a quick query to a small 8B model.
Exactly that. It forces the policy LLM to learn the value of computation, you could say, to internalize the cost.
And there's a way to tune this?
Yep, there's a hyperparameter, they call it alpha, the cost coefficient. It controls the trade-off. You set alpha low, the system mostly ignores cost and just goes for the best possible answer.
Lacks performance.
Right, but if you crank alpha up, you tell it, hey, cost is really important, it'll start prioritizing cheaper routes, even if it means slightly lower accuracy sometimes.
That tunability must be incredibly useful for businesses trying to balance performance and budget.
Absolutely. It lets you dial in the behavior you need.
Okay, so that's the training. How did it actually perform? Does Router R1 live up to the hype in the results?
Well, according to the paper, yeah, it does pretty well. It consistently outperforms strong baselines. We're talking direct prompting, chain of thought, even standard RA systems and those older single-round routers.
Across different types of tasks.
Yeah, 7 different question answering benchmarks. Some were general knowledge QA, like natural questions or trivia QA. Others were complex multi-hop ones, like hop QA and music, where you absolutely need that step-by-step reasoning. Router R1 came out on top.
And did it show that adaptive behavior you mentioned, using more resources for harder tasks?
It did. That was a cool finding. On the multi-hop tasks, the ones that inherently need more reasoning steps, like hop QA, Router R1 automatically ended up making significantly more calls to the external LLMs compared to the simpler general QA tasks.
So it learned to gauge difficulty on its own and decide, okay, this one needs more firepower.
Seems like it, yeah. It escalates resources when needed without being explicitly told, this task is hard.
That's pretty smart.
But for me, one of the most impressive things was its ability to generalize to models it had never seen during training.
Without retraining, how does that even work? How can it route effectively to a model it doesn't know?
It leverages the policy LLM's own understanding. Instead of being hard-coded, the system gives the router descriptions of the available external models right in its prompt.
Just text descriptions, like what?
Simple stuff, like pricing info, maybe typical latency, and a sentence or two about what the model is good at, strong creative writer, struggles with math, that kind of thing.
So if a new model comes out, say LMA3 ChatQA 1.58B, You just add its description to the prompt.
Pretty much. The policy LLM reads the description and figures out, based on its training, where this new tool fits in. Is it cheap and fast? Is it specialized? When should I consider using it?
And they tested this.
They did. They took a trained Router R1, using Quinn as the base, and added 2 unseen models, Palmyra Creative 122B and that LMA3 Chat QA1. Performance either stayed the same or actually got slightly better.
Wow, so the router just figured out how to use the new tools from their descriptions alone.
Yeah, it shows a lot of flexibility. In this crazy, fast-moving LLM world, not having to retrain your router every time a new model drops is a huge advantage.
No kidding. Okay, let's really zoom in on that cost aspect, the alpha coefficient. You said tuning it changes behavior. What did they see when they tweaked it?
Right, the empirical results showed a clear trade-off, just as you'd expect. As they increased alpha, making costs more important, say from 0.6 up to 0.9, the overall task accuracy did gradually drop a bit.
Okay, that makes sense. Prioritizing cost might mean sometimes picking a less capable model.
Exactly. But at the same time, the cost reward went up significantly. The system was successfully learning to be more frugal, to optimize for resource constraints.
It's not just numbers, though, right? This should lead to totally different routing decisions in practice.
Oh, absolutely. The case studies they showed really highlight this. Let's contrast the two extremes.
Okay. What happens when cost is completely irrelevant? Alpha equals 0.
When alpha is 0, the system basically says, money is no object, just get me the right answer. It learned to always call the most powerful and thus most expensive model in the pool. In their tests, that was LMA 3.170B instruct.
Always. Even for easy questions.
Yep. They had an example like finding which of 2 films was released more recently. Sacred Silence or Ekasinati Ek Dewanata. Pretty simple lookup. But with alpha 0, boom, it calls the 70B model. Maximum accuracy, 0 cost consideration.
That's probably how a lot of naive implementations end up working and why the bills rack up.
Precisely. It's the default performance at all costs approach. But now, introduce the cost reward. Set alpha higher. Make cost matter. Alpha 0.
What changes?
The system learns this really important emergent behavior, what they call an escalation strategy.
Escalation. Okay, this sounds like the aha moment. It learns to be cheap first.
Exactly. Take a harder multi-hop question. Example. Find the place of death of Topa Inca Yupanqui's father. Needs connecting facts. With cost factored in, the policy LLM doesn't jump straight to the 70B model.
What does it do instead?
It starts small. It first queries the cheaper, smaller model, maybe LMA 3.1AB instruct.
Okay. And if the AP model can answer it?
Great. Task done, cheap and efficient. But, and here's the key, if the 8B model fails, maybe it says, I don't know, or gives incomplete info.
Then it escalates.
Then, and only then, does the policy LLM say, okay, plan A failed, the cheap tool wasn't enough. It takes that failure information, updates its context,
and calls the big guns.
and then routes the query, or maybe a refined version of it, to the big, expensive LMA 3.170B for the next round.
Ah, so it tries the cheap option first and only uses the expensive resource if necessary.
Exactly. They saw the same pattern on other tricky questions, like one about directors' birth dates for Maker of Men versus Kentucky Colonels. It learns to save the big computational cost for the problems that genuinely warrant it.
That is really powerful. It demonstrates that RL plus this cost reward actually teaches the system intelligent resource management. It's not just static routing, it's dynamic, cost-aware choreography.
Yeah, boosts performance and controls the budget within the same framework. That's the big achievement here.
So wrapping this up, what's the main takeaway for you, the listener, the person building these systems? Router R1 seems to pave a way forward, doesn't it?
It definitely validates this approach. Sequential intelligent routing optimized with RL, including real-world costs. It tackles that non-differentiable problem and delivers, well, state-of-the-art results in the paper.
But there's always a but, isn't there? The sources mention a key trade-off. While it's great on cost and accuracy.
Latency, yeah.
Because it's making multiple calls sequentially, right? Think, route, wait, get info, think, maybe route again. That takes time.
Absolutely. That's the inherent trade-off. A simple single-shot router might give you an answer in, say, half a second. Router R1, to get that better, cheaper answer, might need 2 or 3 rounds.
So maybe 1.5 seconds total instead?
Could be, yeah, depending on the models and the complexity.
Yeah.
So for you, the listener, that raises the crucial question. What do you prioritize?
Is it maximum accuracy and minimum API cost, even if it takes a bit longer to get the answer?
Or do you absolutely need that near instant response and you're willing to accept potentially higher costs or maybe slightly less optimal answers from a single shot approach?
That balance, latency versus accuracy versus cost, seems like the next big challenge in this space. How do we get the best of all worlds?
Exactly. Router R1 shows us how to win on accuracy and cost, but tackling that latency constraint while keeping the benefits, that's where the next innovation needs to happen. It's a fascinating problem to think about.